So that seems pretty good. Semester of subsurface hydrology in 15 minutes. So what's left? What haven't we covered that's in the notes from this year and last? Well, flow nets. This is a flow net. That's pretty much all you have to know about it. But the next time you're asked to analyze flow beneath a dam, you will probably want to make a flow net. Now there are some things that you can actually learn from looking at flow nets, and they do inform you as to how to look at model results a bit better. Those are: equipotentials are most useful when they are equally spaced in head value. That way you can see where the gradient is highest. For instance, under the toe of this dam, or the footing that's going down into the ground, you can see those closely spaced head contours, which is telling you that there's a steep gradient there. Similarly, the flow lines in a quantitative flow net are spaced such that the flow between any two flow lines is the same. So again, right beneath that structure that's under the dam, you can see the flow lines bunching together, and if the medium is homogeneous, you know that right there there's a lot more flow. And if the porosity is constant, you know that the velocity is higher there too. So you may expect to have erosion there, for instance. When you're constructing a flow line, the flow lines themselves are parallel to no flow boundaries, as they would be, and they're perpendicular to constant head boundaries because there's no flow along a constant head boundary. There's no gradient there. They come into something like the water table at an angle, or if the head changes along a boundary, then the flow lines will come across that at an angle. Equipotentials are perpendicular to the flow lines. So that means that equipotentials are perpendicular to no flow boundaries, and they are parallel to constant head boundaries. And note there, that's different than a defined head boundary. I mean where the head value is constant all along the boundary. Now, when I say that this can help you to look at model results, it's pretty natural for a model that outputs head distribution everywhere to contour that with a usual, a constant interval. That's just the way we do things. But if you want to track how water moves through the system, it's also very usual to drop particles and watch those particles move. And these traces give you an idea of the direction that water's moving through the system. But it's important to recognize that if you just randomly place those tracers, or if you don't place them very carefully, in fact, that the things that look like flow tubes are not necessarily flow tubes. So it's harder to interpret the distribution of flow from the contours and tracks of particles than it is from a quantitative flow net. Next up, hydraulic properties. We've talked about things like porosity and hydraulic conductivity, but as a hydrologist, it's really important to be able to relate those to real physical media. So the upshot is, this chart is really handy and you should just memorize it. I like centimeters per second for hydraulic conductivity because you can just remember these order of magnitude ranges for some typical materials, and you can usually place within one order of magnitude or so what a hydraulic conductivity should be. That's really, really useful to be able to do back of the envelope calculations. Again, you can use whatever length unit and whatever time unit you want, but I've found this to be the simplest to deal with. For those of you who like to question why, you can imagine that if you have particles of a certain size, the pores will be related to that size. So if we make the particles smaller, the pores will be smaller, and therefore it's harder for water to flow through that porous medium. Generally, the water is on average closer to a pore wall where it experiences friction, the smaller the pore. So even though porosity doesn't vary with particle size, as long as the particle shapes are the same, the permeability really does. Beyond that, you have to think about the mixture of particle sizes. So if you have a mixture of large and small particles, you end up with even smaller pores, with the small particles filling in those spaces between the larger particles. So it gets difficult if you're thinking of something like a loam that's a mixture of particle sizes. It's hard to interpret what that conductivity might be. There are all sorts of things called pitot transfer functions, some of them very sophisticated, and for the most part they don't really work. They work reasonably well for the soils on which they've been trained, but this back of the envelope kind of order of magnitude understanding of permeability is probably about as good as you're generally going to do. Last but not least, models. It's really difficult to think about quantitative hydrogeology these days without putting it in the context of models. Almost everything we do ends up in a modeling context for analysis. We've done a lot of work with spreadsheet models, so I'll talk about those here. But many of the things that we're learning are really directly transferable to more sophisticated models. So what I like about spreadsheet models is that they're really easy to interpret. Every single cell is just a little mass balance. It's calculating the flow in and the flow out, and in the case of these steady state models, it simply sets the change in storage to 0. So in that way, it's really easy to visualize how hydraulic conductivity in one cell is related to the head in another cell, and how that calculation moves its way through the model. So that's the good part about spreadsheet models. Of course, any of you could tell me the bad things about spreadsheet models. They crash, they're really slow, they sometimes give you results that you just don't understand because you did some silly little thing. So in the end, I hope that the spreadsheet models turn out to be a good educational tool, but I really hope for your benefit that you never ever have to use one again after the end of this class. So that's it, that's all. That's the traditional view of subsurface hydrology, and I hope that it augments what you've been doing with your Soil Buddy.